Hello, I am Dr. Bob. I am going to show you how to install and set up the YUASA Press-Down Test Jig PD. This is the PD. I will be using the motor drive unit DMLHP. We are starting with the two pieces separated as if you have just removed them from their shipping boxes. I place the motor unit on the right with its power cord connection to the back. I place the PD jig on the left with its slider on the right. This is the slider. This is the way the units will be when I connect them, except I will rotate the HP so this side faces the PD. Note that the motor unit and jig could be reversed. I place the jig on the left because it fits better on my bench. If you place the motor unit on the left, keep in mind that some of the video views will be different for you. The motor drive unit DMLHP can be used in the linear reciprocating mode or in the rotary reciprocating mode. This is the linear drive shaft, which is used when the DMLHP is used in the linear reciprocating mode. You install the linear drive shaft through a hole on the motor unit and attach it internally to the linear guide. Only attach the linear drive shaft when it is being used. Make sure you never ship the motor unit with the linear drive shaft attached. You can damage the motor unit and the shaft. This is the rotary reciprocating shaft, which is used when you are using the rotary reciprocating mode. Converting between linear mode and rotary mode is easy. You simply attach or remove the linear drive shaft and set the mode to linear or rotary on the touch panel. Please refer to the DMLHP motor drive unit setup and operation video for information on all the accessories and how to use the DMLHP. That will not be covered in this video. The PD is driven by the linear drive output of the motor unit, so we will be using the linear drive shaft in this video. The following items are parts used to connect the HP to the PD. This is the joint bracket, which attaches to the bottom of the HP. This screw on the PD fits into the joint bracket. The knurled nut locks the PD to the joint bracket. The two screws are used to attach the joint bracket to the HP. This locks the PD to the HP. This is the floating joint which goes on the end of the linear drive shaft and it couples to the slider of the PD jig. Note that this floating joint is different from the floating joint used on the FS and the ST because it is designed to push against the jig. The PD jig consists of the basic jig, contactors, and cartridges. The basic jig includes the slider, the lifter, and the table. The contactor is placed on the lifter and used to make contact with the sample. The sample is placed on a cartridge and the cartridge is placed on the table. I will be using two different types of contactors and cartridges. The standard cylinder contactor has a base or bearing unit and a shaft. The standard plate cartridge is simply a flat base. The second one is an optional three-point bending contactor or elbow-shaped contactor. An optional hold cartridge is used with the elbow contactor, except I will not be able to fit it in at the moment because the contactor is too low. The contactor fits down inside the cartridge, pressing down on the sample. All these items should be in the PD shipping box. The lifter has guiding pins, locating pins, and magnets to make sure the contactor is placed in the proper position. The contactor has guiding holes, locating holes, and magnets to match the lifter. The base simply sits on the lifter. The shaft is shaped like a cylinder with a flat bottom to press against the sample. The top of the shaft is designed to use slotted weights to increase the pressing force on the sample. The shaft simply sits on the base. The cylinder is free to rotate. The cartridge has locating holes and magnets. The table has locating pins and magnets to make sure the cartridge is placed in the proper position. As needed, an adhesive can be used to hold the sample on the cartridge. I find the PD jig very interesting. The other jigs I have made videos for always have a direct link between the drive shaft and the portion of the jig that holds the sample. With the FS, for example, if the drive shaft is moving, the sample is getting folded more or the folding is being reduced. The sample is affected by every movement of the drive shaft. This jig is different. First, this jig works by lowering a weight onto the sample. The drive shaft lifts the weight off the sample. Once the weight is off the sample, further motion of the drive shaft makes no difference to the sample. Even if the contactor moves up and down, it makes no difference to the sample. Likewise, the drive shaft can continue its motion even after the weight is fully on the sample, and the motion of the weight has stopped. Even if the lifter moves up and down, as long as the weight is still in the sample, it makes no difference to the sample. The sample is affected only when the weight of the contactor is on it, and only by the amount of the weight of the contactor. The PD jig works by using a cam on a slider that is pushed or pulled by the drive shaft. This is the cam. As the drive shaft pushes on the slider, the cam moves away from the motor. When the drive shaft pulls on the slider, the cam moves toward the motor. The lifter has a diagonal base that rests on the cam and thus gets lifted by the cam directly according to the movement of the drive shaft. The slider will move away from the motor until the motor reaches its -SP position, which is set by the test machine operator. Then the slider will move toward the motor until the motor reaches its +SP position, which is set by the test machine operator. The slope of the lifter's diagonal base is 0.58, so the lifter moves up or down 0.58 millimeters for every 1 millimeter the slider moves away or toward the motor. Because the maximum motion of the slider is 120 millimeters, the maximum lift is 69.6 millimeters. The normal setting of -SP and +SP will be to have only a small movement of the lifter, moving low enough to get the contactor to rest on the sample, and then moving high enough to get the contactor off the sample. When the contactor is resting on the sample, the weight on the sample will not include the weight of the lifter or even the base or bearing unit of the contactor, only the contactor itself, plus of course any extra weight added to the shaft of the contactor. The cylinder contactor without extra weight is 0.7 kilograms. This is the minimum weight that can be placed on the sample. This is an optional 3-point bending contactor or elbow-shaped contactor. It consists of a double shaft bearing unit, the elbow contactor, and a shaft that is designed to use slotted weights to increase the pressing force on the sample. The double shafts keep the contactor from rotating. The elbow contactor sits on the lifter. An optional hold cartridge is used with the elbow contactor. The flexible sample is held with clamps at the ends. The hold cartridge is shaped to work with the elbow contactor. When the hold cartridge is on the table and the elbow contactor is placed on the lifter, the elbow can press down on the sample. The elbow contactor, actually shaped from a human elbow, causes a flexible sample to bend according to the 3-point bending shape. The elbow contactor, without extra weight, is 2.1 kilograms. This is the minimum weight that can be placed on the sample when using the elbow contactor. Other contactors, like the elbow contactor, can be designed for special purposes. Consider the use of the elbow contactor. As I said, it was designed to match the shape of the bent human elbow. A wearable flexible fabric with embedded electronics will be subjected to various types of flexing. The elbow is one example. It can be straight, but it can be bent significantly. The fabric can be held on the hold cartridge. The elbow contactor can press down on the fabric, and the fabric will take the shape of the contactor. These testing machines typically stress samples with hundreds of thousands or even millions of cycles. The elbow contactor could be used to test a wearable electronic fabric for 1 million elbow pins. Other contactors and cartridges can be designed with special forms. An example could be the platform and plunger from ASTM D4032 for checking the stiffness of fabric by the circular bend procedure. Two other examples could be cone shape or spherical shape. Please contact us if you have needs that are not satisfied with the two contactors that I am using here. The PD uses the same joint bracket as several other YUASA jigs like the FS and ST. In order to install the joint bracket, place the motor drive on its side, not its back. You could damage the connectors. The attachment point is on the bottom of the motor drive, below the linear drive shaft opening. Attach the joint bracket to the motor drive using two screws. The screws may already be in the motor. Tighten the screws with 3.0 Newton meters torque. Attach the linear drive shaft to the HP. Tighten to 9 Newton meters of torque. Push the linear drive shaft into the HP as needed. With the HP turned off, this will be easy. With the HP turned on, you will not be able to move the shaft. I find it easier to attach the special floating joint to the PD slider and then screw the floating joint into the linear drive shaft. Others might find it easier to screw the floating joint into the linear drive shaft first and then attach the floating joint to the PD slider. Tighten to 9 Newton meters of torque using a second wrench so you do not further tighten the linear drive shaft. Push the PD up against the joint bracket with the screw sticking through the joint bracket. It is easiest for me if I leave some room so I can attach the knurled nut to the PD attachment point. Then push the PD all the way against the joint bracket and tighten the knurled nut. Our next step will be to prepare the PD for a sample. I will demonstrate the use of a stylus to press the touch buttons on a smartphone. This will simulate an endurance test of many presses of the button. I have a rather rudimentary setup. I simply removed the top of a ballpoint pen that had a stylus on top, and I used painter's tape to attach the stylus to the bottom of the cylinder contactor. I will put the contactor on the lifter with the stylus. I will place the smartphone on a flat cartridge. The phone is turned on with auto lock set to never. I opened the note and typed the capital letter M a couple of times. Now I will place the phone under the stylus so the key M will be pressed. I will adjust -SP such that the stylus is lifted a small amount above the phone. Set this value on the HP touch panel. I have the lifter as high as it goes, so the setting for -SP is 0 millimeters. I will adjust +SP so the stylus is pressing on the phone's keypad hard enough that the stylus is squeezed to about half its height. By watching the phone as I slowly lower the lifter, I can see when the M is pressed. Stop the lifter at that point. I set this to be the +SP position. It is 10 millimeters. To check, I use jog to move back to -SP, then use jog to slowly move back to +SP. The M has appeared, so the position is correct. I use jog again to move back to -SP. Now I will start the test machine. I am using Flex Data to run the test. I have set the algorithm to run 10 cycles, then stop. No meters are involved. There is nothing to measure. I am looking at a side view of the stylus as it is being raised and lowered. The video insert is looking from above so you can see the stylus being pressed and the M's as they are being typed on the phone screen. I will test an e-textile with the elbow contactor. The e-textile is also a rudimentary sample. I used a stretchable fabric and sewed by hand a non-stretchable conducting thread using a needle. I followed the IPC recommendation and sewed the thread in a zigzag pattern so the fabric can still be stretched without breaking the conducting thread. I put painter's tape on each end of the fabric to make it easier for me to handle it. I need to mount it on the hold cartridge and I need the tape to do that. The tape is on a non-stretching portion of the sample. The elbow contactor will deform the sample in the shape of an elbow. Now I will mount the sample. I wrap each end of the e-textile around a rod and tighten the rod to hold the fabric. The painter's tape makes this much easier. I set this up ahead of time, so I know that the painter's tape needs to be just at the edge of the bottom side of the hole. I want to make sure that the fabric is smooth and only slightly tight. This takes time. You can see why I use the painter's tape. I suspect it will be faster for you. Finally, I have it mounted to my satisfaction, smooth and slightly tight. Here's how the elbow will fit into the fabric. I have the thread off the middle of the fabric so it is directly under the elbow. The elbow will press down on the e-textile and thread and deform them, affecting the resistance of the conducting thread. The elbow contactor is placed on the top of the PD lifter, and the cartridge with the fabric is placed on the PD table. I will use a clip lead on each end of the conducting thread, and I will measure its resistance as the elbow presses into the fabric. I use painter's tape to hold down the clip leads to make sure I do not apply tension to the thread. I will set the top of the movement to be just above the point where the elbow contactor first touches the sample. I set that position as -SP on the touch panel. It is 48 millimeters. I will set the bottom of the movement to be just before the elbow contactor makes contact with the cartridge. I set that position as +SP on the HP touch panel. It is 80 millimeters. I run the jog back and forth to make sure I am happy with the SP settings. Now I am ready to run the test. We will watch the computer screen during the test. I will run the test with flex data on the right side of the screen. I will run one cycle, wait a moment, then run another cycle, doing this for 10 total cycles. You can see that in the algorithm. Repeat 10 times with one position each time. And you can see a live camera looking at the elbow contactor and e-textile sample in the top right corner of the FlexData app. I will monitor the thread resistance with a continuous recording application on the left side of the screen. I have a video insert on the lower right to show the PD test as it is running. I will slowly zoom in. I am running the cycles one at a time because the resistance profile is quite interesting. It has 2 cycles inside every single machine cycle. You can see that on the left side of the screen. As the fabric is pressed down, the resistance initially increases, but then it decreases partway through the pressing. As the elbow is being lifted, the resistance goes through a similar increase and then decrease cycle. That's why I wanted to run 1 cycle at a time, so we don't get confused by the appearance of the resistance waveform. Here's a graph of the resistance. The vertical minor grid lines are 1 second apart. You can see that the movement of the jig is a little more than 1 second, and then the jig is stopped for 3 to 4 seconds. The dip in resistance is near the middle of the movement, so it is happening as the elbow contactor is reaching its deepest point. We note also that the resistance increased cycle by cycle during the test. During the first 2 cycles, the change in resistance was greater than it was during the steady state testing. The conducting thread is twisted fibers. The fibers are probably going through both tension and compression as the elbow contactor is moving, and that no doubt is what is causing the behavior we see in the resistance. The use of a load cell normally would not be needed with the PD because you know exactly what weight you are applying to the sample. There might be occasions, however, when you wish to look at the application of the force. The PD with a flat cartridge does offer an excellent platform to determine setup parameter values of load cells. There are 2 types of load cells that we will examine, a compression load cell and a tension compression load cell. Here's a photo with the compression load cell on the left and a tension compression load cell on the right. Here's the schematic of a typical load cell. Basically, it is a Wheatstone bridge where you apply the input voltage on opposite sides of the bridge and measure the output voltage on the other opposite sides of the bridge. The load cell specifications typically give the sensitivity of the load cell, and often that is about 1 millivolt output voltage per 1 volt input voltage. You need to check the specifications of your load cell to know the limits on the input voltage. For my testing, I can use the plus 5 volt output of the Keithley KTTI GPIB card. The load cell is a linear device, so there are only 2 variables that we need to determine. One is the output voltage when no load is applied, which I will call baseline voltage. The second is the change in output voltage divided by the load, which I will call slope or sensitivity. The equation is quite simple. The output voltage will be the baseline voltage plus the slope times the load. Output voltage equals baseline voltage plus slope times load. Or to determine load, once you know baseline voltage and slope, the equation is load equals output voltage minus baseline voltage divided by slope. The compression load cell gives an output only when the load cell is compressed. The tension compression load cell will give an output when the load cell is being compressed, but also when tension is being applied. Under tension, the output voltage is of opposite polarity. Place the compression load cell on a cartridge on the PD table. Place the cylinder contactor on the PD lifter. We will set -SP to clear the button on top of the load cell and +SP to place the entire weight of the cylinder contactor plus any extra weight to fully rest on the button. I will use 2 weights to do the setup. The cylinder contactor, which is about 0.7 kilograms, the precise value will not matter, and a precision 2 kilogram weight. First, get the output voltage when no weight is applied on the load cell. That value will be the baseline voltage. Then get the output voltage when the cylinder contactor is placed on the load cell. That will be the reference voltage to determine the slope of the output voltage. I like to run 3 cycles and use the middle cycle to make sure I have no starting effects or stopping effects. Then get the output voltage when the 2 kilogram weight is placed on the contactor. The difference in the output voltage before and after the 2 kilogram weight is placed on the cylinder contactor, divided by 2, will be the slope in volts per kilogram. Again, I will run 3 cycles and use the middle cycle to make sure I have no starting effects or stopping effects. Here are the results for the compression load cell. For this test, I am using a unipulse UNLS load cell. Looking at the equations on the graph, we can see that the baseline voltage for this specific load cell was minus 343.5 microvolts, and the slope was 86.2 microvolts per kilogram. Note the step down shortly after the weight is fully on the load cell. This happens when the lifter starts moving back up. The weight is still on the load cell. I suspect this happens because friction from the motion of the lifter is slightly decreasing the weight on the load cell. For the tension compression load cell, first get the output voltage when the load cell is lying on its side. That value will be the baseline voltage. Then place the tension compressor load cell on its end with its top side up and measure the output voltage. Because the load cell has weight, this value will be the reference for placing weight on the load cell. I found that this difference was negligible when using a 2 kilogram weight. As before, I will run 3 cycles using only the cylinder contactor. Then place the 2 kilogram weight on the cylinder contactor and measure the output voltage. Again, run 3 cycles and use the middle cycle. The same equations we used for the compression load cell will be used for the tension compression load cell. I will not measure with tension. I will assume the slope is the same as it is for compression. Here are the results for the tension compression load cell. For this test, I am using a unipulse UNCLB load cell. Looking at the equations on the graph, we can see that the baseline voltage for this specific load cell was minus 122.4 microvolts, and the slope was 45.4 microvolts per kilogram. As was said before, the use of a load cell normally would not be needed with the PD because you know exactly what weight you are applying to the sample. There might be occasions, however, when you wish to look at the application of the force. I will use a sponge, soft sponge, as the sample, which will offer gradually greater resistance to the application of the weight. This is a well-used sponge from my kitchen. I soaked it, then squeezed out all the water, so the sponge is soft, not hard like it was when it is dry. I will use the unipulse UNLS compression load cell. I will run the test with a sample first to see the output of the compression load cell with the sponge. I set the load cell on top of the sponge, centered under the cylinder contactor. I have set minus SP, so the cylinder contactor is a few millimeters above the load cell, which is sitting on the sponge. I have set plus SP, so the full load of the contactor will be on the sponge plus a few millimeters. I will run the motor drive unit at its minimum speed to have the slowest application of the weight. I will run 3 cycles. I like to use the middle cycle as a reference to remove any starting effects or stopping effects. I need to readjust the minus SP and plus SP settings because of the lack of the sponge. It might have been best to simply replace the sponge with a hard object exactly the thickness of the sponge. Now I will run the test without the sample to see the output of the compression load cell to be used as the reference or as the idling data. Here are the results of the test. You can see from the green curve that the load cell with no sample very rapidly shows the change in weight. Looking at the red curve, with the sponge though, there is a gradual increase in output voltage until the sponge has been compressed to its minimum thickness with that specific weight applied. The voltage can be converted to load in kgf, kilograms force, or newtons, by applying the factors obtained in the UNLS microvolt per kilogram graphs shown earlier. 344 microvolts baseline, and 86 microvolts per kilogram load. We can see that the load applied was 0.74 kgf or 7.3 newtons. This is the load from the cylinder contact with no added weights. We have looked at the YUASA PD press-down test machine and how to install and use it. This test machine is very interesting to me because the forces being applied to a sample are dependent on the weights being used and not on the forces being applied by the motor drive unit. We looked at two different types of contactors, a cylinder contactor, which we used with a stylus to press keys on a smartphone, and an elbow contactor, a special shaped contactor we used to press down on an e-textile. We found that the change of resistance of the thread on the e-textile during the test gave us a very interesting curve. Note that other special type contactors could be designed for different types of samples. We used the PD to set up load cells to measure the load being applied to a sample. To do that, we ran a cycle with no sample and then a cycle with a sample. The difference in output is the load applied to the sample. We could also use a tension compression load cell, insert it into the linear drive shaft, and then find the load under both tension and under compression. Again, we would run one cycle with a sample and another cycle with a sample, and the difference in the output voltage of the load cell gives the load applied to the sample. I have found it helpful to run 3 cycles with and without the sample and use the middle cycle of each to make the calculations. That eliminates any effect from being a first cycle or a last cycle. The data from the single cycle without a sample would then be subtracted from the data from every cycle during a multi-cycle test with a sample. We tested a soft but resilient sponge to see the profile of the load on the sample. This concludes the YUASA PD press-down test machine setup video.